So today we're going to be doing our activity having to do with section 11.2. That's our inference for two-way tables using chi-square test for homogeneity and independence. Right, we're going to do a Desmos activity to help do this. As with the last few Desmos activities I've done, the first few slides of that activity are going to be review of the things that we saw yesterday. I also have a short video on how to use the calculator, your yellow calculator. You hopefully have that. So you can practice stuff on that as well. And then we have some problems to solve using our chi-square statistics stuff. All right, so I'm going to put the link for this activity in the chat so y'all can join. Or if you prefer, you are welcome to just go to student.desmos.com and find the AP Stats 11.2 activity. And give me a second for the chat to go. There we go. The link should be coming through for the activity right there. You're restricted to the first screen, which is not a check-in today. It's just the first screen. So please, once you get there, wait there, and we'll get started in a couple of minutes once people have joined the activity. Basic math tells me that there are people in the class that are not in the Desmos activity. Please join the activity. It's better than not joining the activity and not getting the practice. All right, we're going to get started. Where's my mouse? There it is. All right, so first we have our introduction here to section 11.2, inference for two-way tables. Right, we can use a two-way table to summarize data involving two categorical variables. To analyze the data, we compare the conditional distributions of one variable for each value of the other variable. Then we turn to formal inference. Those are chi-square tests. Two different ways of producing data for two-way tables lead to two different types of chi-square tests. The first is the chi-square test for homogeneity. When a study aims to compare the this is a poorly written sentence, I apologize. This is when a study aims to compare the distribution of a single categorical variable for each of several populations or treatments. In such cases, the researchers should take independent random samples from the population of interest or use the groups in a randomized experiment. The null hypothesis is that there is no difference in the distribution of the categorical variable for each of the populations or treatments. The alternative is that there is a difference. We then have the chi-square test for independence. This is when a study is designed to investigate the relationship between two categorical variables, trying to find out if one has an influence over the other. In such cases, researchers take a random sample from the population of interest and classify each individual based on the two categorical variables. The null hypothesis is that there is no association between the two categorical variables. The alternative is that there is an association. Another way to state the null hypothesis is that the two categorical variables are independent in the population of interest. Remember, in statistics, when we talk about things being independent, that means that the one thing does not affect the probability of the other thing. All right, so this is in general what we're doing in section 11.2. One of these two tests, one tests for, if a distribution is different between two populations, and one tests for if two variables are independent within a single population. Right, and we'll get back to the main differences between these a little later on. Next, we have our conditions for performing inference on a two-way table. There are two sets of conditions because there's two different tests. We have the conditions for performing a chi-square test for homogeneity. This one has a different randomness condition than the other two chi-square tests. Right, the data must come from independent random samples or from the groups in a randomized experiment. When it says independent random samples, that means that the You can't be pulling the samples from the same population, because if I pull people from the same population, they're no longer independent. If someone's in one sample, they cannot be in the other sample, therefore they don't have the same likelihood of being chosen, blah, blah, blah. We must be choosing independent samples, which means they're probably coming from different populations or groups. And that's a major difference. Then we have the 10% in large counts condition, which is the same for both. 10% must be checked when sampling without replacement. And large counts, all expected counts are at least 5. Then our conditions for performing a chi-square test for independence, the randomness condition is that the data come from a well-designed random sample, one sample, or a randomized experiment. The way that we find expected counts is the same regardless of the test that we're doing. Right? If we're doing a test for homogeneity or a test for independence, we calculate the expected counts the same way. Right? When the null hypothesis is true, which is the assumption when we're finding the expected counts, the expected count in any cell of a two-way table is the row total times the column total that that cell is in. What row is that cell in? What column is it in? Multiply those totals together, divide by the table total. So when you're finding any set of expected counts, all of your calculations involve dividing by the same number. Whatever that table total is, everything gets divided by that table total. We then have our rundown on the chi-square test for homogeneity. We saw this yesterday. Right, when conditions are met, we use the chi-square test for homogeneity. We have our null and alternative hypotheses, which we write there. And then after writing those, we start by finding the expected counts and calculate the chi-square statistic. The way we calculate the chi-square statistic is the same for all chi-square tests. Observed minus expected squared divided by expected, add all those things up. Where the sum is over all cells, not including totals, in the two-way table. If the null hypothesis is true, the chi-square statistic has approximately a chi-square distribution with degrees of freedom equaling the number of rows minus 1 times the number of columns minus 1. Right, so again, our degrees of freedom with a chi-square test depends on the number of categories. We do not need to consider the size of the samples. Right, it is the number of categories that matters. In this case, it's the number of rows minus 1 times the number of columns minus 1. The p-value is the area to the right of chi-squared under the corresponding chi-square density curve. We also have the same rundown here for our chi-square test for independence. The major difference is that we have a couple different ways we can write our hypotheses. First is we can write the null hypothesis as there is no association between two categorical variables in the population of interest, versus the alternative that there is an association between two categorical variables in the population of interest. Or we can use to write them as the null hypothesis is that two categorical variables are independent, meaning one has no influence over the other, in the population of interest, versus the alternative that two categorical variables are not independent, meaning knowing one thing influences the other. And we do these same exact calculations and steps as we did for the other test. So that is section 11.2 in a nutshell. Next, we got a short video here. It's like 2.5 minutes long, showing you how to use your calculator to find chi-square, to do a chi-square test. Running a chi-square test will give you the chi-square statistic, the p-value, and the degrees of freedom, which can be pretty nice to get all those things in one shot.
This is Lee Natero. In this video, I'll be showing you how to do a chi-square test for a two-way table using the TI-8384 calculator. We'll be using an example that's found in Chapter 11, Section 2 of the Practice of Statistics. In this example, we're interested in seeing if there's no difference in the true distribution of entrees ordered when no music, French accordion music, or Italian string music is being played. To begin, we'll enter our data in matrix A. Hit second, X to the negative 1, go over to Edit, and choose Edit Matrix A. We don't want matrix A to be a 1 by 1 matrix. We want it to be a 3 by 3 matrix. So hit 3, enter, 3, enter. And now we can fill in our matrix. Now that our data is entered, we're ready to run the test. Hit second mode to get back to the home screen. Then hit stat, go over to tests, and scroll to find chi-squared test. I'm going to hit the up arrow since I know chi-squared test is near the bottom. This is a little quicker way to get there. Chi-squared test. And we need to tell the calculator where our observed matrix is stored. It's stored in A, not E. So I need to change this. To change this, hit second, X to the negative 1, and then hit enter on matrix A. The expected counts are going to be stored in matrix B. We'll leave the color as blue, and we'll come down here to calculate. Our chi-squared test statistic is about 18.3, and our p-value is 0.001. This means we have a statistically significant result. So we would conclude that there is a difference in the true distributions of entrees ordered when the different types of music are being played. We also have the option of drawing the chi-squared distribution. So let's go back to chi-squared test again. And instead of choosing calculate, let's choose draw. We can see the chi-squared distribution being drawn, and at the bottom of the screen we see the chi-squared test statistic and the p-value. Because this p-value is so small, we don't really even see the shading in the end of the distribution here.
Are there any questions about the calculator stuff we just saw? All right. So now we're going to actually do some calculations. So we go to the next screen. We have our expected counts that we're going to be calculating. All right, so has modern technology changed the distribution of birthdays? With more babies being delivered by planned C-section, Miss McDonald's statistics class hypothesized that the day of the week distribution for births would be different for people born after 1993 compared to people born before 1980. After all, why would a doctor plan a C-section for the weekend? To investigate, they selected a random sample of people from each of the 2 age categories and recorded the day of the week on which they were born. The results are shown in the table to the right. Is there convincing evidence that the distribution of birthdays has changed? So this will be the context for the next few problems so that we can ultimately try to answer that question. First, we need to calculate the expected counts for the 2 age groups, assuming that there is no difference in the distribution of birthdays. Please round to 2 decimal places. Please note you do have access to a calculator right here at the top of your screen. All right. And for example, I will show you the proper calculation for the first entry on the table here. Right. It's based on the first entry of the observed counts, which has a row total of 21 times a column total of 77 divided by the table total of 150. We get 10.78. That's what goes in here. Right. Then go to the next one. That is in this row again, so we still have 21 times 73 divided by 150. We get the next value. Type it in, and so on. Nope. We're using, so 9 is the second entry, it corresponds to the second entry here, is in the top row, which has a total of 21, and the second column, which has a total of 73. So we do 21 times 73 divided by 150. It will tell you if you have the correct values. Let's take a few minutes and work on these expected values, the expected counts. Please feel free to use a calculator or your own yellow calculators if you have it. We will discuss this in a bit. All right, so on this one, it looks like most of you guys are working on it. Some of you got all of the table completed. Very good. Whether you finished the entire table or not, as long as you were figuring out how to make the calculations, that's the biggest part, right? Also, if you're not rounding properly, you might get marked incorrect, right? So like on this entry here from Monday before 1980, right, we need to have 23 times 77 divided by 150. We get 11.806666666. When I round to 2 decimal places, that rounds to 11.81, not 11.80. You need to use proper rounding rules, right? If the value to the right of where you're rounding to is 5 or more, you round up to the next value. If it's less than 5, you just keep that value there. So if this was 11.804, we would round to 11.80. But that's not the case, so we round up to 11.81. Right. We can find the next one here. Again, the row is the same, column change, so we go to 73 this time. We get 11.19. Again, this one stays the same because the value to the right of the 9 is a 3. That's less than 5. We're good to go. Okay. We can continue down the same pattern here, and we'll get all the expected values, all the expected counts. Do you have any questions about this particular part? All right, so we're going to move to the next part. All right, so the tables pictured to the right show the observed and expected counts. Observed is the first one, expected is the second one. These observed and the expected counts do not match what you found on the previous slide. Someone made a mistake when printing this textbook. They did some incorrect calculation and rounded improperly or something. Some of these values do not match what you guys found. Not sure how that happened. But anyway, for the next part of this exercise, please use the expected counts that are provided. All right. Calculate the chi-square statistic. Please only type the number and round to 2 decimal places. So that means all I want is a value in here. I do not need the chi-square notation thing. I don't need you to show all 14 parts of this calculation, right? Just the final number value and round it to 2 decimal places. This is an opportunity to practice what you saw in the video using the matrices. You will need to use a 7x2 matrix for each of these tables. All right. If you need help with that, please let me know. If you do not have your graphing calculator, this is going to take a little bit longer for you to calculate it because you're going to have to do it one piece at a time using the chi-square statistic calculation. Right, observed minus expected squared divided by expected for all 14 entries. So we'll give you a little bit of time here to work through this, and then we will discuss. All right, that may or may not have been enough time, but that's okay. As long as we're working towards this, whether we finish these problems or not right now, I'm not terribly concerned about. We're going to talk about this. So to do that, I'm going to bring up my calculator here, and we'll go through how to do this. Where's my mouse? There it is. There. All right, so we're going to use the matrices for this because it's essentially the fastest way we can get our results. we want to do this by hand, or each individual of the 14 calculations, it's going to take a minute. It's not efficient, right? That, and when we put this into our calculator, we now have the results for later if we need to come back to that same comparison. We can do other stuff. All right, so where'd I go? We're going to go to second and x minus 1, right? I've got these in here already, but we'll still go in and look at them. So we'll go to edit, right? I already have all of the observed counts in the matrix. This is a 7 by 2, 7 rows by 2 columns. And you can see I have 12, 9, 12, 11, 14, 11, all the values. All right, so this one's ready to go. Now the calculator's kind of smart. And we'll see if it did this again like it did last time. Notice when I put these in, I put in all of our expected counts. Notice that's not what's in my calculator anymore. It actually adjusted all of these expected counts to be what they were supposed to be, which is what you calculated in the previous screen and whoever wrote the textbook made mistakes on. Right, so it actually readjusted all the expected counts to be correct, even though the ones we typed in were the ones provided, which I found out earlier today were wrong in some spots. This corrected it. So that's kind of interesting. I didn't actually have to tell it to do anything. It just fixed it itself. It's kind of weird, but I don't know exactly how it figured that out. But anyway, that being said, we could go in here and put it back to where it was. Right, so we would be 11.78 instead of 11.81, right, and all that stuff. I'm not going to go through and do that because it's not terribly important to get the result, but we have our tables in here. We're ready to rock and roll on this, so now we can use them. So to use them, we go to Stat, and we go over to Tests. Right, it's the little third menu here. And we're going to go down to option C, which is chi-squared test. And I don't want to click too fast because it'll get lost. So there we go, option C, chi-squared test. Your calculator should default to use matrix A and matrix B as the observed and expected, unless you've used this in another class and had other matrices that have been used before. Right? Then it might not be there, but it will default to just use A and B. So it should already be ready to go. You don't have to do anything. Go down to calculate. And there we go. We have our chi-squared statistic of 6.54911, blah, 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 blah. Rounding it to 2 decimal places, we get 6.55. The nice thing is now we already have a p-value and we know the degrees of freedom, even if we didn't calculate those on our own. So that's good too. We already have more values just by putting in our tables. So we have all that. Is there any questions? All right, so we get 6.55. We'll go to the next one. All right. So now we're going to be finding our p-value. All right, so our null hypothesis, no, assuming that you don't have the p-value from the previous calculation. Our null hypothesis is that there is no difference in the distributions of birthdays for people born before 1980 and people born after 1983. The alternative is that there is a difference in the distributions of birthdays for people born before 1980 and after 1983. We found the chi-squared statistic was 6.55. We're going to assume that all conditions have been satisfied. Random 10% large counts, which they have. We're going to use table C to find the p-value, and then we're going to use the chi-squared CDF, or alternatively, if you already did the chi-squared test and you have the p-value, that's fine as well. And so we're going to get these two different values. I have a little section of table C here. I don't know how small or large that shows up on your own screen. It if you need the version of table C, there is a copy of the formulas and tables in the files in our Teams channel, or you can just go into Canvas and find it in there. Or I can drop a link in here, I probably will too. Please note, our p-value from table C is only going to be greater than a certain value. It's not going to be less than something. That is not an accident, that was done purposefully, and I'll get into why shortly. Then you'll put your exact value from the chi-squared CDF function or the chi-squared test on your calculator. I'll give you all a few minutes here to work, and then we'll talk about it. So let's look at this. I'm going to actually bring this guy up. All right, so let's get to table C. There we go. So here on table C, we have degrees of freedom of 6, right? And we have degrees of freedom 6 because we had 7 rows and 2 columns. 7 minus 1 is 6. 2 minus 1 is 1. 6 times 1, 6. Okay, so we have degrees of freedom equaling 6 for this. Now notice in this row, every value is greater than the chi-square statistic we found. They're all bigger than 6.55. So that means 6.55 is somewhere to the left of 7.84. It's somewhere over here. Which then if we follow that up to here for our tail probability P, that means the p-value for that chi-square statistic is greater than 0.25. Because it's somewhere over here, somewhere bigger than that. We do not know what the less than side of that is. It's not on the table, so we're not going to even guess it. We're just going to say, well, we know for sure the p-value is greater than 0.25. That's good enough. And just to show, we could have the same thing happen on the other side of the table, right? Let's see, 1, 2, 3, 4, 5, 6. We somehow get a chi-square statistic that is greater than 24.1. We would then conclude that the p-value is something less than 0.0005. And we wouldn't have an upper bound for that. We just know that's less than something. I'm sorry, lower bound. All right. So that happens with table C sometimes, and that's okay. So we get 0.25. And submitting that one marks this one wrong. I don't know why. And anyway, we found our chi-squared statistic previously. It was 0.3. I forget what this one was. Let's look at the calculator because it's on there. Yep, there we go. All right, 0.36456. So we would could go to 0.3646, right? If we're rounding to 4 spots. I don't know. Did I set this one up to take that? Yes, I did. All right, cool. All right, so that works. If we use the alternative method in the calculator, which would be to use the chi-squared CDF function, which is possible, maybe the chi-squared CDF function will work for the test for goodness of fit as well. So maybe we didn't use the matrices and we didn't do that chi-square test function, right? We can use, we go to our distribution and we go to chi-square CDF right here. And we put in 6.55 as the lower bound, a big number for the upper bound, degrees of freedom 6. And we'll get just a slightly different answer. Really close, but a little different. We get 0.364, and this would round to 0.3645 instead of 3646. Ultimately, this difference between these two methods doesn't create a different result. will ultimately have the same conclusion. Yes? You're supposed to, yes. Oh, he's collecting them? Yeah. Right. If you haven't put your name on the paper, yeah, we gotta put the name on the paper. All right, so yeah, we do get a slightly different response, but ultimately it does not change anything. All right. Any questions on this part? Next. All right, this is important. We need to be able to do this part. So our p-value from the birthday study is 0.3645. We use the one from chi-squared CDF. All right. There's two things to do in this part. Interpret this p-value from the calculator in context. When you're interpreting in context, we're saying, what does this p-value mean in terms of the context we're saying? This does not say make a conclusion. That is the next question. All right. In this question, interpret this p-value. It says, okay, based on the context of this problem, what does this p-value represent? What is this probability for? That's what the interpretation needs to be. The next part is the conclusion. Based on this p-value, do we reject the null hypothesis or fail to reject the null hypothesis? And then what do or don't we have evidence for? All right, so we'll take a couple minutes here to answer these questions, and then we will talk about it. So when we're interpreting a p-value in context, we're interpreting what does this probability mean? All right. And this calculation of this for the probability, for the p-value, is based on the assumption that the null hypothesis is correct, which in this case is assuming that there is no difference in the distribution, or that the distribution of birthdays is the same. Right? And the p-value represents the probability of observing results this large or larger in the distributions of the groups. All right, so that's what p-values represent in any of our contexts from this course. When it says to interpret a p-value is always based on the assumption that the null hypothesis is correct. It's the probability of getting a result the result that we saw or larger, essentially. All right, so assuming that the distribution of birthdays is the same, there is about a 0.3645 probability of observing a difference in the two distributions of birthdays among the two age groups as large or larger than the one in this study. It's a probability. The conclusion is when we compare the p-value to our significance level and decide whether or not we reject or fail to reject the null hypothesis. Right. And so for the conclusion, because the p-value of 0.3645 is greater than alpha equaling 0.05, we fail to reject the null hypothesis. Right? This p-value is really big. It's something that we could expect to see even if the null hypothesis is true. Right? We do not have convincing evidence that there is a difference in the distributions of birthdays for people born before 1980 and people born after 1993. All right, so we have that first statement saying essentially why we fail to reject the null hypothesis, and then that we do not have convincing evidence of our alternative. Right? We need both parts. Simply saying that we reject or fail to reject the null hypothesis is not enough. It's part of it. You need that part, but it's not enough. Are there any questions? Is there anything I can clarify on this part? Okay. And again, I do apologize for the length of this activity, but I do think we need to practice these things. All right, this next screen here is just some information. All right, which chi-square test to use? We have 3 of them that we've seen in this chapter. All right, to help recognize which test to use for a given context, you should think about how the data were collected. Take note of the number of populations or groups and the number of variables. Here's a quick summary. All right, for goodness of fit, this is when we have 1 variable and 1 population. So we collect data, we take a random sample from a single population of interest, and we collect data about 1 variable. For the test of homogeneity, we have 1 variable and 2 or more populations. So we're collecting data about a single variable, but we're sampling independently from several populations, 2 or more. And then our test for independence, we have 2 variables and 1 population. So again, we're sampling from a single population. We're taking a single sample and then collecting data about 2 variables. Right? And we're trying to determine with independence, are these things related? Is there an association between these 2 things? If I know one thing happens within this population, does that mean something about the other thing? Right. The homogeneity is trying to find a difference between these 2 populations. Is there a difference between this thing that I've tracked? Right. Is it significant? Right. So to decide which test to use, it's important to look at how the data was collected, not necessarily just look at the data. We could have very similar data that's collected differently. So we have to be careful of that. So the last things here is a few multiple choice questions. There's 3 of them, the 3 different contexts here. Carefully read the 3 given contexts below and select the appropriate chi-square tests that should be used. You do not need to perform any calculations or actually perform the significance test. Just choose the right one. Let's take a few minutes here and choose the appropriate test. I'll talk about these. So our first context there, we have a random sample of 1,000 adults. Was asked whether they regularly attend religious services and whether they drink alcohol daily. Right, so we have a single sample. Why did you do that? I closed you. Right, we have a single sample that is then categorized by 2 responses, 2 variables. That is a test for independence. It even says they're trying to determine if there is a relationship between these things. Trying to find a relationship is trying to find an association, right? This next one, right? We have 2 populations, the US and Canada, that are sampled from independently. And then they collect data about a single variable, right? Quality of life relative to what it was before they had their heart attack. Right? That is a test for homogeneity. 2 separate populations being sampled from and a single variable that we're checking. Trying to find a difference between the populations. The last one, we have a single population that's being sampled from, the offspring of these pairs of flies, and a single variable that is being collected, and that is eye color and wings. That's being grouped together as a single thing because there's certain combinations that we can have, and we're going to keep track of the number of flies that have those specific combinations. That is a test for goodness of fit. 1 population, 1 sample, and 1 variable. Right? Does the observed thing match what we think it should have been? Right. So those are those ones. Is there any questions here? So the test for independence if you see them say, is there a relationship between this and this? That's a clue that you're doing a test for independence. When you're trying to see if two things affect each other, you're trying to determine, are these independent variables or are they dependent? Do they affect each other? That's a test for independence. When it comes to the test for homogeneity, we're looking for, is there a difference? Asking about, is there a difference between these two populations when we track this variable? Right? All right. So, where's my mouse? There it is. And we'll stop that. All right. So again, I do apologize. That was a much longer class than I normally do. But I wanted to make sure we got through all this practice. There's a lot of things going on in these problems now, and we have to practice them. If you do have any questions, comments, concerns, obviously let me know. I'm happy to help. I still have my office hours on Mondays. If you guys want to do that. But otherwise, send me emails, send me things you need help with. All right. Besides that, I hope you have a great rest of your day, and we will see you next week.